Welcome to our comprehensive guide on electrolysis, tailored for ICSE Class 10 students. Electrolysis is a fascinating chemical process that uses electricity to drive a non-spontaneous chemical reaction. In this video, we'll break down the core concepts, explore real-life applications, and guide you through the essential details you need to ace your exams. Whether you're new to the topic or looking for a thorough revision, this journey will help you understand electrolysis from the ground up. Let's begin by understanding what electrolysis is and why it's so important in both science and industry. Electrolysis is the process of using an electric current to break down a compound into its constituent elements. This process typically occurs in an electrolytic cell, where two electrodes are immersed in an electrolyte solution. When electricity passes through the solution, chemical changes occur at the electrodes, leading to the decomposition of the compound. This is a key concept in chemistry, as it allows us to extract elements and understand the movement of ions. Let's now look at the basic setup required for electrolysis. Electrolytic cell is made up of three main parts: the electrolyte, the anode, and the cathode. The electrolyte is a substance that conducts electricity by the movement of ions. The anode is the positive electrode, while the cathode is the negative electrode. When the electric current is applied, positive ions move toward the cathode and negative ions move toward the anode. This movement of ions is what drives the chemical reactions during electrolysis. Understanding these components is crucial for grasping how electrolysis works in practice. Electrolytes are substances that, when dissolved in water, produce a solution that conducts electricity. Common examples include acids, bases, and salts. In electrolysis, the electrolyte allows the flow of electric current by providing ions that move toward the electrodes. The choice of electrolyte affects the products formed at the electrodes and the efficiency of the process. For example, using sodium chloride solution will yield different results compared to using copper sulfate solution. Let's explore how ions behave in an electrolytic cell. During electrolysis, positive ions known as cations migrate toward the cathode, where they gain electrons and are reduced. Negative ions called anions move toward the anode, where they lose electrons and are oxidized. This movement is essential for the chemical reactions that take place at each electrode. The overall process results in the decomposition of the electrolyte into its constituent elements or compounds. Understanding the movement of ions helps explain the changes observed during electrolysis experiments. Electrolysis involves two key types of reactions: reduction and oxidation, collectively known as redox reactions. At the cathode, reduction occurs as cations gain electrons. At the anode, oxidation takes place as anions lose electrons. These simultaneous reactions are fundamental to the process, enabling the separation of elements from their compounds. Redox reactions are not only central to electrolysis, but also to many other chemical processes in daily life and industry. Uncommon application of electrolysis is the decomposition of molten ionic compounds. For example, when molten sodium chloride is electrolyzed, sodium metal is produced at the cathode and chlorine gas at the anode. This process is widely used in industry to extract metals from their ores. The absence of water ensures that only the ions from the compound participate in the reaction, making the process straightforward and efficient. Electrolysis can also be performed on aqueous solutions, where water is present along with the dissolved compound. In such cases, both the ions from the compound and water can undergo electrolysis, leading to a variety of possible products. For instance, electrolyzing aqueous copper sulfate produces copper at the cathode and oxygen at the anode. The presence of water adds complexity, as it can be reduced or oxidized depending on the condition. Classic experiment in electrolysis is the decomposition of water into hydrogen and oxygen gases. When a small amount of acid or salt is added to water to increase its conductivity, passing an electric current through the solution splits water molecules. Hydrogen gas collects at the cathode while oxygen forms at the anode. This experiment demonstrates the basic principles of electrolysis and is often performed in school laboratories. Electrodes are crucial in electrolysis. They can be inert, like platinum or graphite, which do not participate in the reaction, or active, like copper, which can be involved in the chemical changes. The choice of electrode affects the products formed and the efficiency of the process. Inert electrodes are often used when the electrolyte's ions are the only participants, while active electrodes are used when the electrode itself is meant to react. Let's look at the electrolysis of copper sulfate solution using copper electrodes. At the cathode, copper ions gain electrons and deposit as copper metal. At the anode, copper atoms lose electrons and go into solution as copper ions. This process is used in electroplating and purification of copper. The reactions at each electrode are clear examples of reduction and oxidation in action. Electroplating is a practical application of electrolysis, where a thin layer of metal is deposited onto another object. For example, silver plating involves using a silver anode and the object to be plated as the cathode. When current passes through the electrolyte, silver ions deposit onto the object, creating a shiny protective coating. Electroplating is widely used in jewelry, cutlery, and electronics industries. Electrolysis is also used to purify metals such as copper. In this process, impure copper is made the anode and pure copper is the cathode. As electricity flows, pure copper is deposited at the cathode while impurities fall away or remain in solution. This method ensures high-purity metals for industrial use, making electrolysis an essential technique in metallurgy. Beyond the classroom, electrolysis plays a vital role in industry. It's used to extract metals like aluminum and sodium, produce chlorine and hydrogen, and manufacture chemicals. The process is scalable, allowing for large-scale production of essential materials. Understanding the industrial applications of electrolysis highlights its significance in modern society and technology. Several factors influence the outcome of electrolysis, including the nature of the electrolyte, the type of electrodes, the concentration of the solution, and the applied voltage. Each factor can change the products formed and the efficiency of the process. For example, increasing the voltage may lead to the formation of different substances at the electrodes. Understanding these factors is key to mastering electrolysis. Faraday's laws of electrolysis describe the quantitative relationship between the amount of substance produced at an electrode and the quantity of electricity passed through the electrolyte. The first law states that the mass of a substance produced is directly proportional to the charge passed. The second law relates the masses of different substances produced by the same quantity of electricity. These laws are fundamental for calculating yields in electrolysis experiment. To determine the amount of product formed during electrolysis, you need to know the current time and the substance's equivalent weight. Using Faraday's laws, you can calculate the mass of metal deposited or gas evolved. This is especially useful in industrial settings where efficiency and cost-effectiveness are crucial. Practicing these calculations will help you excel in your exams and understand real-world application. Electrolysis of sodium chloride or common salt is a key industrial process. When molten, it produces sodium metal at the cathode and chlorine gas at the anode. In aqueous solution, the products can vary depending on the conditions. This process is essential for producing chemicals like caustic soda and chlorine, which are used in many industries. Brine is a concentrated solution of sodium chloride in water. Electrolysis of brine yields three important products: chlorine gas at the anode, hydrogen gas at the cathode, and sodium hydroxide in solution. This process is widely used in the chemical industry and is a classic example of how electrolysis can produce multiple valuable substances from a single process. Lead bromide is another compound that can be electrolyzed in its molten state. At the cathode, lead metal is deposited, while bromine gas is released at the anode. This process demonstrates the extraction of metals from their salts and is an important example in the study of electrolysis for ICSE students. Extraction of aluminum from its ore, bauxite, involves the electrolysis of aluminum oxide dissolved in molten cryolite. This process, known as the Hall-Héroult process, is energy-intensive but essential for producing pure aluminum metal. The use of cryolite lowers the melting point, making the process more efficient. This is a prime example of electrolysis in large-scale metal extraction. Electrolysis isn't just for laboratories and factories. It's used in everyday life, from the production of batteries to the purification of drinking water. Electrolysis-based devices can remove impurities, generate gases for medical use, and even help in cleaning jewelry. Recognizing these applications helps you appreciate the relevance of electrolysis beyond textbooks. Batteries operate on principles related to electrolysis. In rechargeable batteries, electrolysis occurs during charging, revealing the chemical reactions that happen during discharge. Understanding electrolysis helps explain how batteries store and release energy, making it easier to grasp the science behind everyday gadgets like smartphones and laptops. Electrolysis is used in water purification systems to remove contaminants and disinfect water. By passing an electric current through water, harmful substances can be broken down or removed, making the water safe to drink. This application is especially important in areas where clean water is scarce, highlighting the practical benefits of electrolysis. In the medical field, electrolysis is used for various purposes such as sterilizing equipment and generating medical gases like oxygen and hydrogen. It's also used in certain cosmetic procedures such as hair removal, where a small electric current destroys hair follicles. These applications show the versatility of electrolysis in improving health and hygiene. Safety is paramount when performing electrolysis experiments. Always wear protective gear such as gloves and goggles and work in a well-ventilated area. Handle chemicals and electrical equipment with care and follow your teacher's instructions closely. Being aware of potential hazards ensures a safe and successful learning experience. Students often make mistakes such as confusing the anode and cathode or misidentifying the products formed at each electrode. It's important to remember that the anode is positive in electrolysis and to carefully write the half reactions for each electrode. Double-checking your setup and calculations can help avoid these common errors. Half reactions show the changes occurring at each electrode during electrolysis. At the cathode, reduction occurs so electrons are gained. At the anode, oxidation occurs so electrons are lost. Writing balanced half reactions helps you understand the overall process and predict the products formed. Practice is key to mastering this skill. Predict the products of electrolysis. Consider the ions present in the electrolyte and the reactivity of the elements involved. The more easily reduced or oxidized species will react at the electrodes. For example, in aqueous sodium chloride, hydrogen is produced at the cathode instead of sodium because hydrogen ions are more easily reduced. Understanding these trends helps you answer exam questions accurately. Electrolysis processes can have environmental impacts, such as energy consumption and the release of gases like chlorine. However, advances in technology are making electrolysis more efficient and environmentally friendly. For example, using renewable energy sources to power electrolysis can reduce its carbon footprint. It's important to consider these factors when studying industrial applications. Electrolysis is at the heart of many green technologies such as hydrogen fuel production. By splitting water into hydrogen and oxygen using renewable electricity, we can produce clean fuel for vehicles and power plants. This application demonstrates how electrolysis can contribute to a sustainable future and reduce our reliance on fossil fuels. Pairing electrolysis with renewable energy sources like solar or wind power enhances its environmental benefits. This combination allows for the production of green hydrogen, which can be stored and used as a clean energy source. As technology advances, electrolysis will play an increasingly important role in the global shift toward renewable energy. Discovery of electrolysis dates back to the early 19th century, with scientists like Michael Faraday making significant contributions. Faraday's experiments laid the foundation for our understanding of electrochemical processes. Learning about the history of electrolysis helps appreciate the scientific progress that has shaped modern chemistry. School laboratories, electrolysis experiments are a hands-on way to observe chemical changes and reinforce theoretical concepts. Simple setups using beakers, electrodes, and power supplies allow students to see gas evolution, metal deposition, and color changes. These experiments build practical skills and deepen understanding of the subject. Writing balanced chemical equations for electrolysis reactions is a key skill. It involves identifying the ions present, writing the half reactions, and combining them to form the overall equation. Practicing this process helps you understand the underlying chemistry and prepares you for exam questions. Electrolysis is only possible with ionic compounds, as they contain charged particles that can move and carry current. Covalent compounds, on the other hand, do not conduct electricity in solution and cannot be electrolyzed. This distinction is important for understanding which substances can undergo electrolysis. Conductivity of an electrolyte depends on the concentration of ions in solution. Strong electrolytes like sodium chloride dissociate completely and conduct electricity well. Weak electrolytes like acetic acid only partially dissociate and have lower conductivity. This affects the efficiency and outcome of electrolysis experiments. Electrolysis is the reverse of what happens in electrochemical cells like batteries. In electrochemical cells, chemical energy is converted to electrical energy. In electrolysis, electrical energy is used to drive chemical changes. Understanding this relationship helps clarify the broader field of electrochemistry. Redox potential of ions determines which reactions occur at the electrodes during electrolysis. Ions with higher reduction potential are more likely to be reduced at the cathode, while those with lower oxidation potential are oxidized at the anode. This concept is essential for predicting the products of electrolysis in complex solutions. In preparing for exams, focus on understanding the principles of electrolysis, practicing chemical equations, and memorizing key definitions. Pay attention to the differences between molten and aqueous electrolysis and be able to write half reactions for common compounds. Reviewing past papers and practicing calculations will boost your confidence and performance. Let's look at some sample questions. What are the products at each electrode during the electrolysis of molten lead bromide? How does increasing the concentration of an electrolyte affect the process? Practicing such questions helps reinforce your understanding and prepares you for the types of problems you'll encounter in exams. Recap: electrolysis is a process that uses electricity to drive chemical reactions, breaking down compounds into their elements. It involves electrolytes, electrodes, and redox reactions. Applications range from metal extraction and purification to electroplating and green technology. Mastering the basics and practicing calculations are essential for exam success. Electrolysis has a profound impact on our daily lives and the world around us. From the production of metals and chemicals to advancements in clean energy, this process is at the heart of many technological innovations. Understanding electrolysis not only helps you in exams but also gives you insight into the science shaping our future. If you're interested in learning more, explore textbooks, online resources, and practical experiments related to electrolysis. Delving deeper into the topic will enhance your understanding and may inspire you to pursue further studies in chemistry or related fields. Stay curious and keep exploring the wonders of science. Congratulations on completing this journey through electrolysis. With a solid grasp of the concepts, applications, and calculations, you're well equipped to tackle exam questions and appreciate the role of electrolysis in the modern world. Remember, chemistry is not just about memorizing facts, it's about understanding the principles that drive the world around us. Keep learning and stay inspired.